Good day, Professor Emi Longo. My name is Vikesh Rampasad, student number 159358868. This is my water infrastructure and resources management project for module code WRM3701, assessment number 4, unique number 823802. What follows is the presentation of my analysis report of the water supply project to the five townships in the Tsitsipe local municipality. This report is for the Tsitsipe local municipality, and it has been prepared by Vikesh Rampasad Consulting. Vikesh Rampasad Consulting has been appointed as the civil engineering consultants to analyze a water supply project to be implemented by the Tsitsipe local municipality in line with its water services development plan. The municipality contracted Vikesh Rampasad Consulting to analyze the water supply project and submit a report detailing the following: the number of pump stations required, the storage capacity of the bulk reservoir, the head loss for each component, the hydraulic profiles for the pumping mains and pipe sizes, the hydraulic profiles for the gravity mains and pipe sizes, and to evaluate the need for pressure and surge control. Additionally, Vikesh Rampasad Consulting is to make a short presentation on the technical report. This is that presentation. The project is intended to provide water supply to the five townships as shown in the locality map below on the screen. The water supply scheme will obtain water from the Nyangwe River via an abstraction works plant at the river. The water will then be pumped from a pumping station via pumping main to the water treatment plant for purification. From the water treatment plant, the water will be pumped from a pumping station via pumping main to a bulk storage reservoir on Shikahilo Hill. The bulk storage reservoir will provide 8 hours of supply without pumping as per the local municipality specifications. From the bulk storage reservoir, gravity mains will supply the water to the local supply reservoirs, referred to as the demand centers at each of the five townships. This is the general layout of the five townships, showing the Nyangwe River, the pumping mains to the water supply treatment plant and the bulk storage reservoir, and then the gravity or bulk mains all the way down to the demand centers 1 to 5. The methodology of analysis: EPANET software will be used to analyze and size the water supply components, and literature reviewed as described in the section 2. Literature review will guide decisions regarding the water supply project. The literature reviewed is aimed at sourcing technical literature corresponding to all the components of the water supply project and to aid input into the EPANET software, as well as aid the drafting of specification and guiding of decisions regarding components which EPANET is unable to provide. Furthermore, some of the literature reviewed, example, the source, the water treatment marks, water treatment works, etc., will not have a direct bearing on the findings of of the technical report, but have been included to provide reference and background to the findings of the technical report. Methodology: EPANET software will be used to analyze and size the water supply components with regards to hydraulic profiles of the gravity and pumping mains and the head loss for each component. Literature review described in section 2, as well as directives from the municipality, will guide decisions regarding the number of pump stations required, storage capacity of bulk service reservoir, and the need for pressure and surge control. A short presentation, which this is will be uploaded to the YouTube channel, and this is the link to that channel. This is the overview of the EPANET process, steps 1 to 9, which is all the way from the setup of the water supply network on EPANET, the adding of pumps, stations and pumps and tanks with capacities, i.e. the bulk service reservoir, all, and adding time patterns for peaks and time settings for hydraulics, time settings and time durations, and adding hydraulic settings and pump curves all the way to running the program on EPANET. The first iteration was to use 300 millimeter diameter pipes in the EPANET, and I will now switch over to EPANET to show you how this is. This is the EPANET program. We can see my network has been set up. All the pipes are 300 millimeter diameter pipes, as you can see. with the correct lengths and all the pipe properties and pump properties and tank capacities have all been input. I will now run the analysis. Warning messages were generated. These are the warning messages, which shows that there are negative pressures and so and max and at the demand centers. My legends have been set up so to indicate excessively high pressures and negative pressures in red at the nodes, as well as velocities in the pipes above 1.5 meters per second. I will now run the animation video, and you can see a lot of the pipes and demand centers have negative pressures and velocities above 1.5. What needs to be done is to increase the pipe sizes to reduce the velocities in the pipes. And this will be my next iteration, which I will now set up and then run that iteration for you in Ethernet. This is my next iteration on Ethernet. You see I've increased the rising mains to 900 millimeters diameter pipes. I have increased the gravity bulk mains to 650s, 550s, 400s, etc. I will now run the analysis. You'll see it is successful, showing that there were no negative pressures. I've set the legends up again to show negative pressures and excessively high pressures at the nodes in red, as well as velocities above 1.5 in red. I'll now run the animation video. You'll see that none of the velocities in the pipes are above 1.5, and that all the pressures at the demand centers are all positive, none of them negative. This says that the pipes are satisfactory with regards to maximum velocities in the pipe as well as the pressures at the demand centers. My next step is to determine whether the head loss in the pipes not were acceptably within the allowable limits, which was 10% of the available head. I'll now return to my project in which I do this calculation to determine whether these pipes satisfy that requirement. This is my calculation to determine whether that iteration satisfied maximum allowable head losses in the pipes. As you can see from my calculations, some of the pipes were undersized with regards to head loss. They exceeded the allowable head losses. So these pipe sizes needed to be increased, and then the head losses to be checked to to satisfy the requirement to be less than 10% of the allowable head losses. I'll now return to Ethernet with the second revised pipe size. This is my Ethernet third iteration. We have revised the sizes to satisfy the losses, maximum head losses allowable in the pipes. You can see that some of the pipes have increased by an increment of 50 millimeters. I will now run the analysis. See, once again, it is successful. In running the animation time series video, you can see that the legends have been set up to again show negative pressures or excessively high pressures in red, and then the velocities above 1.5 in red. You'll see through the time series that none of the pressures and velocities show a problem, and then now the head losses for this will be checked and determined, and if it's satisfactory, this will be my solution and proposal for the bulk supply network in the Tshipi local municipality. I'll now return to my project report and show you the calculation for the head losses. This is the check for the allowable head losses in the pipes under my third iteration, and you can see all the head losses are within the acceptable or allowable limits, and so these pipe sizes will be what I propose for my bulk water supply network. Again, so having shown that this network satisfies head losses requirements, this will be my proposal, and this will be the file which I emailed to Professor Emalungu. This is my final Ethernet solution. Now, in my report, the results of the different iterations were discussed, showing the 300 millimeters, which fails for maximum velocities and pressures, The second iteration was successful, but proved to be unsuccessful in regards to head losses. And then finally, my third iteration satisfied all the requirements. Uh, in section 4, these are all the results in pipe velocities and hydraulic profiles of the pipes as per my third iteration and solution. Under the discussion section of my report, uh, we discussed that the essence of this project is to source water from Nyangwe River, a low point, and to pump it to the water treatment plant, and then to eventually gravitate it to the bulk service reservoir. The storage reservoirs and pumping mains and pumps inputs were as per the specifications from the local municipality. For the water to be adequately supplied to the demand centers from the bulk storage reservoir, the velocity and head losses in the pipes and pressures in the demand centers must be within the acceptable range as follows. The water velocities in the pipe must be equal to or below 1.5. The head losses in the pipe should be less than 10% of the available head loss. The pressures at the demand centers cannot be negative. As per the continuity equation, the amount of water is a constant, and therefore to Q equals V times A, and therefore to decrease the velocity, the area needs to increase, and that means an increase in pipe size. Uh, Also, as the water flows through from the bulk through the pipes, the water flow in the pipes loses hydraulic head due to friction in the against the pipe walls. Different pipes materials have different friction coefficients. Additionally, small pipes of the same material have larger friction coefficients of the same material. Thus, loss of hydraulic head due to friction translates to loss of hydraulic pressure at the demand centers. Again, when the pressure is too low or negative at the demand centers, the pipe diameters would have to be increased. Also, if the head losses in the pipes are too much, head loss as a function of length as well as velocity and diameter of pipes. And to decrease the head loss in the pipes, the velocity, the diameter of the pipes would also have to be increased. Constant, Consequently, we had a first iteration of 300 millimeter diameter pipes, which didn't satisfy maximum velocities and pressures. Our second iteration satisfied velocities and pressures, but the head losses were too much in a few of the pipes. And then finally, on our last iteration, we satisfied head losses, maximum losses allowable, as well as velocities and pressures. In conclusion, we are going to use two pumping stations with pumps able to deliver 600 liters per second against 80 meter head, a storage capacity of the bulk server reservoir of 10,244 cubes to supply 8 hours of water without pumping. Uh, our hydraulic profiles and sizes of our rising and bulk mains are 900 millimeters, combination of 900 millimeters, 650, 500s, 550s, and 400, etc. Hydraulic profiles are as the results in the report. Pressure surges can develop due to pump startup and shut off, and so we recommend pressure relief valves should be installed on pumping points to avoid damage caused by pumping against closed valves. This is my solution to the Tsitsipe local municipality. This is the report and as well as the EPANET uh, uh, file for their use. Um, I thank you very much for the opportunity to present this. And if there are any questions, the contact details of Vikesh Rampasat is on the cover page, and you're welcome to ask direct questions. And I thank you very much for attending this presentation, and I wish everybody a pleasant day further. Thank you.